Hi. So in the previous video, you might have seen how to solve a given problem based on Nyquist criteria and how to comment, a stability related, result for a given problem. So anyway, in this problem, let us look into a new problem now. Now there is a small changes which I have done. You will realize what we are trying to, what I am trying to say for you. Okay. So let us start solving problem step by step. You will come to know what is the changes between this and the previous video problem. Okay. First step is we need to check whether is there any pole at the origin. We don't have any pole at the origin in this particular problem. Therefore, I will directly write the basic contour diagram. So the basic contour diagram is what I'm going to write here, which we saw in the previous two videos, both the videos. Okay. Now you'll have a semicircle here. You'll have A. This is B, C, D, and then this is plus J infinity, and this is minus J infinity, and this is 0 degree and 360 degree. This is 180 plus and 180 minus. Okay, this is plus 90 degree and this is minus 90 degree. Okay, and we have this R tending infinity. Okay, now this is a basic contour for this particular problem because we don't have any pole at the origin. Now, the next step is we need to write the pole zero diagram. So plot the pole zero diagram and then check is there any pole towards right half of S-plane. If you look into the roots here, we have a 0 here, which is minus 2. And we have two different roots which are poles which is equal to minus 1 and plus 1. So therefore, I'll draw a pole 0 mapping. And we see that we do have one pole is minus 1 is one pole. We have 0 at minus 2. We also have another pole which is plus 1. So this is the changes which I was telling you. See, we do got one pole which is towards right half of S-plane. Therefore, the capital P value which we used to discuss earlier, that becomes 1. So the capital P value is equal to 1. So this says that the system, this says that the open loop system is unstable. Why it is unstable? Because capital P is not equal to 0. Okay, keep that in mind. Now let us go move on further in next step. So what we need to do is contour or conformal mapping. So contour. In this problem, the contour is A, B, C, D, A. Okay. So contour is A, B, C, D, A. Now let us go with section 1. So section 1 is AB trace. So for that, let us take the problem again. So we have G of S into H of S equals S plus 2 divided by S plus 1 into S minus 1. So put S equals J omega. So I will be getting G of J omega into H of J omega equals J omega plus 2 divided by J omega plus 1 into J omega minus 1. So what we need to do is we need to write in terms of magnitude and phase. So therefore, the magnitude here for this particular J omega plus 2 is root of omega square plus 2 square is 4, and angle is tan inverse of omega by 2. And next one is angle is tan inverse of omega by 1 is omega, and the next one is tan inverse of minus omega. Okay, now this is equal to square root of omega square plus 4. Anyway, magnitude for this tan inverse J omega plus 1, I think I did not write here. Sorry, so let me write the magnitude first. So here, tan inverse of root of omega square plus 1 is the magnitude for J omega plus 1. So this is root of omega square, again plus 1 because minus 1 the whole square is plus 1 only, into tan inverse of minus omega. So now what happens? Let me write the magnitude all separately, angle all in a separate manner. So square root of omega square plus 1 into omega square plus 1 into tan inverse of omega by 2 in the numerator, tan inverse of omega in the denominator. See, tan inverse of minus theta can be written as 180 minus tan inverse of theta. Keep that in mind. This is in trigonometry, allied angles and all. We'll see this. Tan inverse of minus theta can be written as 180 minus tan inverse of theta. So here tan inverse of minus omega can be written as 180 minus tan inverse of omega. So this entire thing is angle. This entire thing is magnitude. Now let us substitute omega value at A and B. So at A, omega equals 0. Therefore, the magnitude will be equal to 0 square root of 4 divided by root of 1 into root of 1. So root of 4 is 2. Whereas angle will be tan inverse of 0 is 0. This tan inverse of 0 is 0. This tan inverse of 0 is 0. But we have 180 in the denominator. If it goes to the numerator, it becomes minus 180. So this is the value at A. Now when I go with that B, where omega equals infinity, at B omega equals infinity, I will be getting infinite square plus 4 is infinite divided by infinite square plus 1 is infinite, infinite square plus 1 by infinite. So here, what we get here is infinity divided by infinity into infinity into tan inverse of infinity divided by tan inverse of infinity into 180 minus tan inverse of infinity. So what do we get here is one infinity and another infinity gets cancelled, so you will get 1 divided by infinity, which is equal to 0 at an angle. Tan inverse of infinity is 90. Tan inverse of infinity is 90 minus 180 minus 90. So here, if you see this problem, the minus 180 plus 90, sorry, because see, this is 180 minus 90, so if it goes to the denominator, this becomes plus 90. So 190 and another 90 will get cancelled. Minus 180 plus 90 is minus 90. So therefore, this becomes 0 at an angle minus 90 degree at B. So at B, 0 at an angle minus 90. At A, it is 2 at an angle minus 180. And if I take these two values and try to draw the trace of the linear contour, I'll be able to see that the magnitude at A equals 2, but angle is minus 180, and angle minus 180 will come this side. Okay, angle minus 180 is this. And let me take, this is the point where the distance is 2 at an angle minus 180. And this point is actually A dash. Now when I go with 0 magnitude, it means it is at the origin. It is at the origin. But as if you see here, the angle is minus 90 degree. So minus 90 means if this is 0 degree, if you go from bottom, this becomes minus 90 degree. So from A to B, from A it should start at minus 180, and when it meets B with magnitude 0, it should end at minus 90 degree. So therefore, the trace is from A dash minus 180 degree to B dash at 90 degree. So this is the trace in this direction. Okay, this is the trace we have got between A dash to B dash. So the direction of arrow will be towards B dash. Okay. So at A we had magnitude 2 at an angle minus 180 degree. So that is what I have written. The distance is 2 towards minus 180 degree. Whereas at B the magnitude is 0. So it becomes at origin. The magnitude is at origin. Whereas minus 90 is this line, this angle. So therefore, if I want to trace, draw the trace of the counter, I should start from A dash and I should end at B dash at 90 degree. So start at 0, minus 180 degree, end at minus 90 degree. Now let me go with next section 2, which is tracing the path BCD. The path BCD. So for this, we need to make a note of the question which is given. So which is g of s into h of s. So first of all, we'll write the question given, which is g of s into h of s equals s plus 2 divided by s plus 1 into s minus 1. S plus 1 into s minus 1. So if you go back and see, The question is s plus 2 divided by s plus 1 into s minus 1. So what we do here is we'll first substitute, s as r into, so it is limit r tends to infinity r into e power j theta. So this is the substitution for s we need to make. So what happens for this g of s and h of s is now g of r into e power j theta into h of r into g power j theta equals limit r tends to infinity. So r into e power j theta plus 2 divided by r into e power j theta plus 1 into r into e power j theta minus 1. As we know, r tends to infinity, so r into e power j theta will be very much higher than 1. So I can write this as limit r tends to infinity. So r into e power j theta plus 2 can be just written as r into e power j theta, because 2 is very less compared to r tending towards infinity. And in denominator, we get r into e power j theta into r into e power j theta. Okay, so this term will become just r into e power j theta, because r is infinite, so 1 is very less. Even here minus 1 is very less, so you will be remaining with r into e power j theta. So if you see here, one term r into e power j theta gets cancelled. So therefore, we do have limit r tends to infinity 1 divided by r e power j theta. Now this finally what I'll do is I'll write this as limit r tends to infinity. I'll take the magnitude part separate, which is 1 by r. And if I take this angle which is in the denominator, if I take it to numerator, it becomes e power minus j theta. Okay. Now, if I substitute r equals infinity, and we know according to the basic basic Nyquist counter, the angle at B is plus 90 degree, the angle at C is 0 degree, the angle at D is minus 90 degree, the angle at D is minus 90 degree. So if I substitute that, what I get is if r tends to infinity, 1 over infinity is 0. So the magnitude part becomes a 0 here at an angle. When theta is plus 90, the angle is minus 90. And when theta is 0, it is 0. When theta is minus 90, the angle becomes minus of minus 90 is plus 90. So this is the angle. So what is that this says here is, at B, the magnitude is 0, angle is minus 90. At C, angle is 0 and also magnitude is 0. Whereas at D, angle is 90 degree, whereas magnitude is 0 at an angle 90. So if I try to write the trace for this particular BCD path, I'll be getting trace in this way. So all three magnitudes are 0. So all 3 points will lie on the origin, because 0 is the magnitude. So B dash, C dash, D dash, all 3 lies at the origin. Whereas for B dash, the angle is minus 90 degree. For C dash, it is 0 degree. Whereas for D dash, it is, minus 90 is, this is plus 90 for D dash, minus 90 is for B dash, minus 90 comes at the bottom. So this is the trace for the path BCD, and I'll just write this as B dash, C dash and D dash. Okay, we finish the trace for B dash, C dash and D dash. Now we'll try to go with tracing for, D to A. As I already told you in the previous video while solving the previous problem, the trace for D to A will be, the mirror counter of the trace A dash to B dash that we have written. So therefore, I'll try to write from D to A counter here itself. So for D to A counter, so this is the line. Okay. Now I do have D to A. So this is your D dash. This is the position D dash, and this is the position A dash. So D to A is the mirror counter of A dash to B dash. See the semicircle at the bottom, the mirror counter of that will be from D dash to A dash in this way. So the direction is from D dash to A dash will be towards A dash. So I hope you got it. Now we'll mix all these three traces, this, and we'll check what is the final Nyquist contour that we get. So I'll try to write the final diagram here. So I'll try to write the trace, A dash to B dash, and then D dash to A dash. And this distance what we got was equal to 2. Okay, so this is A dash. So this is B dash, C dash, D dash. So this trace is A dash to B dash, and this trace is D dash to A dash. So this is 90 degree, minus 90 degree, magnitude is 0 here, whereas this is minus 180 degree angle. Okay, so this is the final Nyquist contour trace for this particular problem. Now somewhere, see the distance is 2, it means that minus 1 plus 0j point will be here. In the left half of S plane, your minus 1 plus 0j point is here. Now in this problem, you are able to see that the encirclement n is equal to how many circles you can see which is covering minus 1 plus 0j. It is one circle, one single circle. So therefore, encirclement n equals 1. Now n is plus 1 or minus 1. See the direction of the encirclement. It is anti-clockwise direction. So the arrow is going in this direction and this arrow is coming in this direction. That is, as it is anti-clockwise direction, n will be negative 1. N will be negative 1. So now, if you see, initially what was P that we calculated, P was 1 and n is minus 1. N is minus 1. Therefore, my Z equals P plus n, where P was 1, n is minus 1, so Z is equal to 0. So you should be able to understand this. Our system was unstable for open loop, but as Z equals 0, the system now is stable for closed loop. Stable for closed loop. So therefore, the transfer function which is given to you, this transfer function is actually unstable for open loop, but it is stable for closed loop. So this is what the plus point of finding Z. Okay. So the system was unstable for open loop, but it is stable for closed loop. This is what Nyquist stability criterion is important for. I hope you understood this problem and also the previous problem in the previous video, and you were able to see the difference between two different problems. Okay. Let us see another type of problem in the next video. Okay. Thank you.